Good morning everyone, Dr. Nat here. So we are continuing on Module 11. This is part number 4, I believe. So we will continue on that. So we were discussing last class on how to choose the appropriate null hypothesis to answer the right question. And this was example number 2. We already discussed example number 1 and hopefully everyone understood what was being said. So the question goes, specifications for a water pipe call for a mean breaking strength of mu of more than 2000. So they don't want the mean breaking strength to be equal to 2000. They want it to be more than 2000. So if we were to answer this type of question, we would say that, oh, this is the alternate hypothesis. The thing that we want to answer is typically the alternate hypothesis. But again, whenever you have the equal or unequal, you have to follow those first. For example, the null hypothesis will always have equality, whereas the alternate hypothesis will always have the inequality. And if you were to look at the question, you would answer what they want to know as your alternate hypothesis, if that makes sense. Okay, so the engineers want to know, they want to perform a hypothesis test to decide whether or not to use a certain kind of pipe. So they selected a pipe. They want to know if this pipe is can withstand a mean breaking strength of more than 2000 pounds per linear foot. So this was our first formulation, whereby the mu is less than or equal to 2000 versus H1, the alternate hypothesis, the mu is greater than 2000. This is what we want, right? So what happens if we were to reject this, and what happens if we were to accept this? So if we were to reject this, we would say, oh, okay, so the mean breaking strength of this pipe is actually greater than 2000, which is good, right? Versus if we were to accept the null hypothesis, what this implies is that the mean breaking strength is equal to 2000, and also below that, it can also be below 2000, which is bad and is a recipe for disaster. So this was the first formulation, and this is what we discussed last time. So what would happen if we were to use a different formulation for the hypothesis? For example, the null hypothesis, we are specifying the mu to be greater and equal to 2000. Just now, it was less than and equal to 2000. And then H1 is mu less than 2000. What would it imply if we were to accept or reject the null hypothesis? So let me use my pen. Is this my pen? Why is it looking like this? Okay, I think that is the marker, sorry, the highlighter. So if I were to reject this, right, it means that my pipe has a mean breaking strength of less than 2000, so I will not use the pipe, not use it, because it's not what we want, right? Whereas if I were to say that the null hypothesis is accepted, or it is plausible, it is equal and also greater than 2000. I'm not accepting this, I'm accepting this as my truth, which means that the mean breaking strength is equal and also greater than 2000. These are the possible values for the mu. So if H0 is not rejected, the engineers conclude that mu might be greater than or equal, but that it also might not be. So again, they won't use the pipe. So why wouldn't they use the pipe? I think this sentence is a little bit confusing. So again, they won't use the pipe because they need the mean breaking strength to be greater than 2000, not greater and equal. So whichever hypothesis that we accept, the engineers won't be able to use the pipe. So not a really good test, I would say. Okay, moving on. So what is the relationship between hypothesis testing and confidence interval? So if you noticed, when we were talking about the p-value, the p-value somehow or rather looks like the confidence interval, right? But in Okay, let's talk about the confidence interval. When we were talking about the confidence interval, let's say the confidence interval of 95%. So I wanted something within this region, right? Because 95%. And the confidence interval will give me a range of the mu. Versus the p-value is here. The p-value is located at the edges of the distribution, not in the inside. Remember, if our null hypothesis is over here, then we are looking at this region. If the null hypothesis is here, we're looking at this region. If the null hypothesis is here, we're looking at this region. Basically, whatever the alternate hypothesis is talking about. So in a hypothesis test for a population mean mu, we specify a particular value of mu, which is the null hypothesis, and also determine whether that value is plausible, which was what we were doing just now. This sort of gives us the risk level, right? The p-value tells us how probable something is, and that is the function of our hypothesis test. So a confidence interval, on the other hand, for a population mean mu, can be thought of as a collection of all values for mu that meet a certain criteria of plausibility. And again, we're talking about the range here, specified by the confidence interval 100 times 1 minus alpha. So we're going to look at alpha more closely. So the values contained within a two-sided 100 times 1 minus alpha confidence interval for a population mean mu are precisely those values for which the p-value of a two-tailed hypothesis test will be greater than alpha. Okay, so what does that mean? Let's see, using an example. So we are talking about a sample mean lifetime of 50 microjoules. This is the sample mean, 12.68. I believe we have seen this example. And the standard deviation was S equals to 6.83. This is the sample standard deviation. And then we would set our significance level, alpha, to 0.05. The 95% confidence interval for the population mean lifetime mu was computed to be this range. So if I were to draw this, the 95 for a two-sided confidence interval, this would be the 95%. And for my alpha to be 0.05, this would correspond to the 2.5% and 2.5%. This is for a two-sided, okay? So the range of the mu can be between 10.79 and also 14.57. And whatever the mu is, it is going to be at the midpoint. So suppose we wanted to test the hypothesis that mu was equal to one of the endpoints of the two-sided confidence interval. I think I should draw this more nicely. I think there's a picture coming. Okay, so let's go for that. So suppose we wanted to test the hypothesis that mu was equal to one of the endpoints. So we want to test, is mu really this value? Let's try to prove that. So here our hypothesis is mu equal to 10.78. We are going to assume this is true versus our alternate hypothesis where mu is not equal to 10.79, which is not part of the confidence interval. So under null hypothesis, the observed sample is 12.68, comes from a normal distribution with mean 10.79 from here, and standard deviation, we were given our S value as 6.83 and our sample size 50 microdrills, so this is square root of n. So you would get this guy, the standard deviation of the sample mean, as 0.9659. So using this, we calculate what is the z-score. So this is our sample mean minus the mu divided by this guy over here. We've seen this equation many times already. So the z-score is 1.96. So this would correspond to a p-value of, so here we have it here, so 0.025. So a z-score of 1.96 gives us the probability of 0.025 using the CDF table, right? So 1 minus whatever the value that we get from the CDF table for 1.96. And for this guy, minus 1.96, we would get this value directly. So adding these p-values up, we would get this as 5%, which means that this is 95%. It all balances out. So since the null hypothesis specifies that mu is equal to 10.79, both tails contribute to the p-value, which is 0.05, and thus equal to alpha. So should we accept or reject this hypothesis? Dun, dun, dun. So our hypothesis was, is our mu part of the confidence interval range? The answer is yes. So mu can be 10.79 because this example is actually proving that the hypothesis test p-value has a relationship with the confidence interval. This is what the example is trying to tell you. Okay, so what if we looked at the other range? So we were talking about the confidence interval being from here and here. So what if we chose this? And of course our alpha must be 5%, because it has to like reciprocate with the confidence interval value. So what we want to prove, if mu is indeed within this range, and we take the endpoint of this confidence interval, which is 14.57. If I were to test this, 12.68, I'm just going to repeat this process again, minus 14.57 divided by, do we have the same standard deviation? Yes. Do we have the same sample size? Yes. So I can still use this value. So I would get 1.96 minus. So since this is a two-sided confidence interval, I would have to look at both sides anyways, which is the same as this guy. So we have proved that the mu is indeed part of the confidence interval, and the p-value alpha is equal to the, our p-value is alpha, right? It is the same alpha as the confidence interval. Okay, so it all checks out. So for your group project, you don't have to actually go for a two-sided hypothesis test, meaning to say you can go for mu 10 or mu greater equal to 10, mu less than greater to 10. For example, you want to go for these guys, so obviously you're not going to get a two-side hypothesis test, right? You're going to get one-sided either on the left or on the right. So you can do that, and if you want to do the one-sided hypothesis test, you would have to know how to do the one-sided confidence interval and relate that to your hypothesis test. So these are the notes that you should refer to. Okay, so we are moving on to hypothesis test for a population proportion, which I have promised to teach you. A hypothesis test for proportions are similar to those for population mean. They are exactly the same except for a few formulas that we need to be aware of, but the rest of the process is exactly the same. So here is the summary for population proportion hypothesis test. Let X be the number of successes in n independent Bernoulli trial. So n is our sample size. And then from this sample size, we determine how many achieved success or achieved fail. So let's say that number is X, and the way that we will calculate P is X over n. So this is the success over the sample size. Okay, so this X follows a binomial distribution, meaning to say there's success and also fail. only two outcomes, remember. To test a null hypothesis of the form as the following over here, assuming that both n times the population proportion and n1 minus population proportion are greater than 10, this is our assumption, compute the z-score as the following. So our z-score previously for mean was like this, right? It was like this, whereby this is the sample mean minus the population mean, and this is our sample mean standard deviation. So this is our sample proportion minus the population proportion divided by the standard deviation of the proportion of the standard deviation of the, what do you call this, proportion, standard deviation, sample proportion, standard deviation. Excuse me. So compute the p-value. The p-value is an area under the normal curve which depends on the alternate hypothesis as the following. So this is exactly the same as the mean that we have seen earlier. So if our H1 has a greater sign, then you would look at this side over here, area to the right of Z. If the alternate hypothesis has a less sign, you would look at here. If the alternate hypothesis has an unequal sign, you will look at both sides because your null is over here. Okay, so you are always going the opposite of the null. So let's see how we can use this equation. So example, a supplier of a semiconductor wafer claims that of all the wafer that he supplies, no more than 10% are defective. He's saying that no more. So hopefully I get this syntax correct. No more means not equal. No more. So 10%, less than 10%. So this is what, is P, not X. So P is less than 0.1, no more than 10%. I hope this is correct. So a sample of 400 wafers is tested. So I'm assuming this is the sample size, 400. And 50 of them, or 12.5%, are defective. So our P sample is 0.125. How did we get this value? It is 50 over 400. I think so. 50 divided by 400. Yes, it's 0.125. Okay, so this is our hypothesis. We want to conclude if the claim is false. So this would be our alternate hypothesis. So this is going to be our null. This is going to be our alternate hypothesis. I hope so. So no more than 10%. No more. So it can be 10, but it can't be more than 10. Okay, so I think I got it incorrect just now. So no more means 10% is part of the range. No more than 10, but 10 is okay. So P is less than or equal to 0.1, and the alternate hypothesis is this guy. Okay, so let's see. So the claim is that P is less than or equal to 0.1. Since our hypothesis concerns a population proportion, it is natural to base the test on the sample proportion given by P hat. I'm going to call this guy as P hat, or the sample proportion. Since the sample size is large, we have 400, right? So this follows the central limit theorem, whereby the proportion will follow a normal distribution given by this. This is the proportion, and this is the variance of the sample proportion. Okay, and this is what we're testing. Okay, so I'm going to erase this. So again, this is our proportion and this is the variance. When we are using for when we are trying to find the z-score, we would want to use the standard deviation, right? So we are going to have to square root this guy over here. So what would that give us? So square root of 2.25 times 10 to the minus 4. How did we get this value? The variance of p hat is p 1 minus p divided by n, and p is 0.1 times with 1 minus p, which is 0.9, divided by 400. And this would give you an answer, which is 2.25 times 10 to the minus 4, if you calculate this correctly. And then obviously you want the standard deviation, so you're going to get the square root of this guy, which is 0.015. So the observed value of the p hat, which is the sample proportion, is the number of success over n, sample size, which is 0.125. We already discussed this. And the z-score would be p hat minus the population proportion divided by the standard deviation of the variance over here. Variance of p hat. Okay? So, oh sorry, squared. So basically it's just this guy lah. Okay, so p hat minus the population proportion divided by the standard deviation of the sample proportion. So this is the formula, and we know that our p hat is 0.125 x over n, remember, minus with the population proportion. Remember our hypothesis tells us that this is what we're testing, the null hypothesis, and divided by our standard deviation of the proportion sample proportion. So you would get this as 1.67 z-score, and looking at your CDF table, you would get, so our H, this is our null hypothesis, right? This is our alternate hypothesis, 0.1, which means that we are looking to the right of our normal distribution over here. Okay, so z-score of 1.67 corresponds to a probability of 0.0475. It's kind of close to 5%, right? So do we accept or do we reject this hypothesis? Okay, so what if we changed our success to 49 instead of 50? Just now we said that the supplier claimed that the probability of the semiconductor chips to be defective is less than or equal to 0.1. And when we sampled the supplier's chips, we found out that we had 50 defective chips out of the 400 sample that we took. So it was 50 over 400. What if we sampled again and we got the value to be 49 over 400? This would give us a percentage of 12.25 instead of 12.5. So this would change our values a little bit, right? So let's see. If our p hat is 0.1225, this also means that our z-score is going to change. This guy is going to stay the same because this deals with the population value, except for this. This is p1 minus p, right? And this is n. So this doesn't change. What is changing is p hat, the sample proportion. And this affects our z-score. So our z-score is now 0.1225, which is p hat minus the population proportion. And the standard deviation of the sample proportion is still the same. So this would give us a z-score of 1.5, which corresponds to a p-value of 0.668. So now it is 6.68%. So if you were deciding to cancel the supplier, cancel in the sense of, getting angry at him, but when you try to sample again, you get your success as 49 out of the 400 samples, you found out that the p-value is now greater than 5%. So do you get angry at the supplier, or do you accept the null hypothesis? So here we have demonstrated the weakness of this rule. So based on the difference of one wafer, 50 versus 49, it could change the results of whether you are going to reject the null hypothesis or accept the null hypothesis. So when you find yourself in this situation, for example, your group project, you found that the p-value is around 4.8, right, which is close to 5%. So what do? Do you accept the null hypothesis or do you reject the null hypothesis? So my advice is for you to resample again. Take another 30 sample out of the 59 population. Okay, so hope that helps. So this is also why the p-value should be reported and not just the statistical significance. So it helps us to know whether the p-value is super close to the statistical significance, and if it is close, we would want to resample again. Okay, let's go for an example here. So a study presents a method for measuring orthometric heights above sea level for a sample of 1225. So this is our sample. Baselines 926 gave results that were within the class C spirit. So this is our success, I'm assuming. 926. And then can we conclude that this method produces results within the tolerance limit more than 75% of the time? So we want to know the probability that this is 75 or 0.75. So I would assume this is the alternate hypothesis because this is what we're trying to answer. And also there's no equality in this statement. Let me rewrite that somewhere else. So our null hypothesis is P, which is less than or equal to 0.75. And then our alternate hypothesis is P greater than 0.75. Okay. So this is what we're testing. Can we conclude that this is the case? So again, we have 926 out of 1225, which is a great number. It follows the central limit theorem, follows a normal distribution. So I can say that, this guy over here follows a normal distribution whereby the proportion is just the population proportion. And this is P1 minus P. This is the variance over N. So what is P? The P that we're testing, we follow the null hypothesis. We assume this is true unless we prove it otherwise. So 0.75 is the closest to H1. So this is going to be 0.75. So 0.75 times with 1 minus 0.75, which is 0.25, divided by 1225. So this is our variance for the p hat. Okay. So what next? We have to find out what is our z-score, right? But I need to know what is my standard deviation first. So we have to square this guy over here. So let's go for the solution. So I'm squaring the variance, and I get the value as 0.0124. I'm sorry, I'm just lazy to calculate using my calculator. So the variance for this guy is 0.0124, I believe. Okay, so what is the next step? The next step is to calculate the z-score. Whoops. Okay, the z-score. So the z-score is p hat minus p population over the standard deviation of p hat. So this would be, we did not calculate p hat yet. P hat, so this should be part of this guy over here. So 926 over 1, 2, 2, 5. So this is the variance. Okay. This is the standard deviation. I'm getting confused here. I'm so sorry. Okay, back to this guy over here, because now we can start. So 926 over 1225 is going to be 0.75, 0.756, 0.756 minus with the population, which follows the null hypothesis, divided by, oh, this guy over here. So this would give me a z-score of 0.48, which corresponds to a probability of 0.3156. Very, very high. Not very, very high, but quite high. And of course, using the threshold or the significance level of 5%, we would not reject the null hypothesis. So what does this tell us? We cannot conclude that the method produces good results more than 75% of the time. We are accepting the null hypothesis, which means that it is going to be less or equal to 0.75. Pretty easy, right? Just have to remember the steps. Okay, so we were talking about proportions. We were talking about means and the relationship with confidence interval. What about proportions? So remember in module number 10, we were talking about proportions having this equation. We called this as the modified P, or the modified proportion, and we called this as the modified sample size. Why did we have to modify the sample size and the proportion? Because this was an approximation that was needed to eliminate the bias. Because if we were to use the original equation, it was complicated and they wanted to simplify the equation, but that simplified equation had some bias to it, so they had to correct the bias by modifying the P and the N. So what does this does this affect our hypothesis testing relationship with the confidence interval? So a level 101 minus alpha confidence interval for a population mean mu contain those values for parameter for which the p-value of a hypothesis test will be greater than alpha. So we know what confidence interval is. It gives us the range, right? So for the confidence interval for a proportion presented in module 10, the hypothesis presented here in module 11, this statement is only approximately true. It is not exactly true like what we described for hypothesis testing the mean with the confidence interval. That one was exactly true. The CI would correspond 1 minus alpha. The alpha was exactly the alpha that we saw in hypothesis testing. So they were completely related and they are true. But for hypothesis testing with proportion, with the confidence interval, the relationship is only approximately true because of this modification. Okay? So if you remember, the methods presented for confidence interval for proportions are slight modifications of a more complicated confidence interval method for which the statement is exactly true. So if you were to describe your relationship between your proportion hypothesis testing and the confidence interval, you can describe the relationship, but you would have to emphasize that it is only approximately true. Okay? Alright, so next, moving on to large sample test for the difference between two means. So the aim is to know whether the means of the two populations are equal. So this is going to be the hypothesis test now. So we are going to sample from two independent populations. We would get a sample mean from each population and we would want to find what is the difference. And we would always want to find out if they are equal or not. So if mu x is equal to mu y, the difference between them would be equal to 0. So this is going to be our null hypothesis, or vice versa. So this is the aim here. If the difference is far from 0, we will conclude that the population mean are different. If the difference is close to 0, we will conclude that the population mean might be the same. Possible, right? So let the random variable x up to xn and y1 up to yn be large, greater than 30, because we want to follow the central limit theorem. And standard deviation, we have the means mu x, mu y, standard deviation of x and standard deviation of y. Assume that the samples are drawn independently. They come from different populations. To test the null hypothesis of the form, this form, so it can be less than or equal to 0. It can be greater than or equal to 0. Or it can be equal to 0. So they have this delta sign over here, which means that it is a small value related to 0. For example, you can test it to be 0.1, which is quite close to 0, right? Delta means small change. Small change that is related to 0. Okay? So compute the z-score. How would we compute the z-score? So for mean, we saw that, I'm just going to try to relate this every time. So we saw that this was the equation for our mean z-score, right? And then we had our z-score for proportion, which was p hat, p population divided by p standard deviation. And for the z-score for the difference between two means, it would be the sample mean minus the x sample mean minus the y sample mean minus 0, or whatever that you're testing. If you're testing it to be 0.1, then you would specify 0.1, but most of the time it would be 0 lah. And then divided by, this is your standard deviation. We have seen this equation before. Again, you don't have to remember, but make sure it's in your cheat sheet. And then if you don't have this value, you can approximate it with the sample standard deviation. So this is also the same as the mean and also the proportion. If you're seeing a greater sign, area to the right. If you're seeing a less sign, to the left. If you're seeing an unequal sign, then you would see a two-side test, right? Okay, let's go for this example. A production manager for a manufacturer of industrial machinery is concerned that ball bearings produced in environments with low ambient temperatures. What does this mean? It means a low temperature. Basically, we don't need this ambient word. So in the morning or at low temperature, the ball bearings that they produce have smaller diameters than those produced under high temperatures, or like during the lunch hour, because at high temperature, right? So she samples 120 ball bearings early in the morning and finds their mean to be 5.06 millimeter, 5.068, and the standard deviation as such. She independently samples 65 ball bearings manufactured during the afternoon and find their means to be this one and the standard deviation to be 0.007. So how can these two populations be independent? Because they are under different condition. One is early in the morning and the other one is in the afternoon. So if we were to try to relate with our project, if we wanted two different populations, we would sample one from CCSE and another one from the electrical engineering department. Why would that be different? Because you don't enroll for the same courses, you learn different things, so you are different populations. Okay, so she samples 120 ball bearings that were manufactured early in the morning, and this, let's try to write this down. So we have our NX as 120, and then the mean diameter, which is sample mean X, 5.068, and then our NY is 65 ball bearings. Sorry, I forgot to mention this one. The S for X is going to be 0.011, and then for ny is 65. For y sample mean, it is 5.072, and then our sy is going to be 0.007. Okay, so she wants to know, can she conclude that the ball bearings manufactured in the morning, which is, we decided that this would be x, so she wants to know if mu x minus mu y, so if mu x have smaller diameters than mu y, so this would be less than 0. Okay, so this is what we're trying to answer, and this would be our alternate hypothesis. So what would be our null hypothesis? It would be mu x minus mu y would be greater or equal to 0. Okay, so this is the sample size, and this is our hypothesis that we already discussed. Since they have a sample size that is large, they would follow a normal distribution. So mu x, the difference between mu x and mu y would just be mu x minus mu y, and the variance is the variance of the sample mean plus the variance of the sample mean y. So if I were to expand this, this would be, if you still remember, of course you still do, so it is going to be it is going to be variance over n. This is going to be variance of x over n, variance of y over n. If we wanted to know what is the standard deviation, we have to square root the whole thing. Okay, so the null distribution is given by this guy over here. We're testing the null hypothesis. The null hypothesis is assumed to be true. Therefore, we are testing the mu x minus mu y to be equal to 0. This is the value that is closest to h1, but still within h0. And then for this guy over here, we just use this equation. What was it just now? 0.011. That was s. So square this over our 120. And this would be 0.007 if I'm not mistaken, over 65. This would be a square, and you would have to square this whole thing. And then the difference between the sample mean x and sample mean y is 5.068 minus 5.072. This is the value that you would use in your z-score. So this is x minus y minus with your small value or 0 divided by the divided by the standard deviation of this distribution, which is 0.001327, and you would get a z-score of minus 3.01. And then that would correspond to, first of all, I need to decide whether I'm going to look at the right or at the left of my normal distribution. So look at my h1, it has a less sign, so I'm looking at the left. So this is where I should look at, not here. No. Okay, so z-score of minus 3.01 is 0.0013, very, very small. I think this is 0.13%. So we can actually reject. No, this is not reject. We can actually reject the null hypothesis, and we can conclude that yes, our mean diameter for the ball bearings produced in the morning is indeed smaller than the ones produced in the afternoon, because the difference between them is less than 0. This guy is small. Okay, so the manager's suspicion is correct. The bearings manufactured in the morning do have a smaller mean diameter. Okay, next example. The article effect of welding procedure on flux cord steel wire deposits compares the properties of welds made using carbon dioxide as a shielding gas with those welds made using a mixture of argon and carbon dioxide. So one welding uses CO2, the other one uses argon plus CO2. So one property studied was the diameter of inclusions, which are particles embedded in the well. So how were they going to test this out? The difference between the properties of the weld. So they were looking at the property which is the particles embedded in the weld, which is the diameter of the particle. So a sample of 544 inclusions in wells, let's just say this is called the sample. 544 sample made using argon shielding plus CO2 is 0.37 micrometer in diameter. Is it micro? Yes. With a standard deviation of this guy, a sample of 581 sample in wells made using carbon dioxide shielding averaged in 0.4 micrometer in diameter with standard deviation of this guy. So NX is 544, our X mean is 0.37, our standard deviation X is 0.25, and then our NY is going to be 581, our Y mean is going to be 0.4, and our standard deviation is going to be 0.26. So what's the next step? Form our hypothesis. So we are trying to conclude that the mean diameters of inclusion differ between the two shielding gas. Differ. This is what we're trying to prove here. So this will be our alternate hypothesis. So our alternate hypothesis is going to be mu x minus mu y is going to be not equal to 0 because they are not equal or they differ from each other, and this is what we're trying to prove. Therefore, this is going to be our null hypothesis, equals to 0. So after you have formed the hypothesis, you would go for the z-score. So how do you know what is the z-score? First, you need to find out what is x minus y. 0.37 minus 0.40, that would give you 0.03. And then you would want to know what is your standard deviation for the x and y. So I'm not going to do that here, no space. So sample size is this. We have formed this hypothesis earlier on, and we want to know what is our variance or standard deviation. So this is the formula that we should use, and this is what we would get, and we would get the square root of this, and this is what we're going to put in our z-score. So 0.03 x minus y minus 0, because this is what we're trying to test for the null hypothesis, divided by the standard deviation. Divide equals to minus 1.97, and this corresponds to a value. First of all, I'm going to look at which side am I looking at. I need to find out both sides, this guy and this guy. Okay, so 1.97 and plus 1.97. So 1.97 corresponds to 0.244 and minus 1.97 is 0.244. The p-value will be the addition of these two guys times 2, so you will get 0.488. So if we are following the 5% significance level, I would reject the null hypothesis. Moving on, we were testing about the difference between two means. Now we're testing between two proportions. Again, the same process, finding the difference and then finding out the z-score and reading the p-value and then reject or accept, right? And the regions that we should look at is exactly the same. If you have this greater sign, for the alternate hypothesis, you look at the right region, less sign, left region, unequal sign, then you are looking at both sides or two-sided hypothesis, two-sided p-value, and you have to add these two values together because they are the sum. Okay, so let x follow a binomial distribution with nx as the sample size and px as the proportion, and let y follow a binomial distribution with ny as the sample size and py as the proportion. Assume that there are at least 10 successes and 10 failures in each sample. So it has to be, it can't be really small. It can't be really small p's, is what they're trying to say. At least 10 in each sample, and that x and y are independent. So if we were to follow the central limit theorem, we know that the sample size must be greater than 30. But they have another condition to use this equation, which is at least there has to be 10 successes and 10 failures in each sample. Okay, so to test a null hypothesis of the form as the following with equality signs, compute our sample proportion for x, which is the success over the sample size, and the sample proportion for y, which is the success over sample size of y. And then the estimate for these two, the sample proportion estimate for these two is x plus y, which is the success in sample x, success in sample y, divided by the sample size, the total sample size. So compute the z-score, you would be computing this minus this divided by this 1 minus this 1 over nx plus 1 over ny. So slightly complicated because of this guy over here. Otherwise, it looks pretty okay to me. I think this one, we don't have a value that we are the minus 0 is not there because obviously we want to test the difference. I'm not sure why it's not there like the mean, but it's okay. Okay, moving on to the first example. The article Survey of Risk Management in Major UK Companies reports that the results of a survey in which managers were asked which methods played a major role in the risk management strategy of their firms. In a sample of 43 oil companies, so they surveyed 43 oil companies, 22 told them that risk transfer played a role, while in sample of 93 construction companies, 55 reported that risk transfer played a major role. So we would say that this is our PX, right? And 22 is considered the success out of the sample size, and PY would be 55 over 93. They are two different populations because one is oil company, the other is construction. And then how would we calculate our P hat? This would be x plus y divided by the total sample size, and x plus ny. So this is 22 plus 55 divided by 43 plus 93. So you would get this value and then use it in your z-score. Okay, so can we conclude that the proportion of oil companies that employ the method of risk transfer, the proportion of oil companies, so we are saying that X that employ the method of risk transfer is less than the proportion. So PX minus PY is going to be less than the proportion of construction companies. So this is going to be our alternate hypothesis, and the null hypothesis is going to be this guy over here. Oops, not that. It has to be the opposite of this. Okay, so this is our hypothesis. What is the next step? The next step is finding out what is our variance, the standard deviation to use in our z-score. So this is the equation. So P hat times 1 minus P hat times with this guy. So that would give me something like this. So I'm going to cheat a little bit. So this is our Px, Py, and then this is our hypothesis, exactly the same that we formed just now. And then I would want to calculate the standard deviation, and they have already did that here, which is 0.0914 is the standard deviation. So this is going to be px minus py minus 0. Okay, so the equation in the summary, they excluded 0, but it's there. But it doesn't really mean much, right? So px minus py minus 0. Px minus py is this guy. So this is what we're getting that value from. Then divided by the standard deviation that we have calculated. Not really, but yes, this is the value. So the z-score would be minus 0.87, and we are looking at the left side. Okay, so the left side is 0.1922, which is quite high, 19.22%. So I would not be rejecting the null hypothesis. What is the null hypothesis? That the oil companies have a proportion of risk transfer less than the null hypothesis is the oil company risk transfer is greater than the construction companies. So I'm not going to reject that, which means that we are not accepting this conclusion. Okay. So that was the end of part 1 of our lecture. I'm going to continue with this in part 2. So I'll see you in part 2.